Okay, so the next theorem is going to be a fundamental theorem. It's going to allow us to compute the size of the Galois group of the normal extension. And the theorem says if we have a finite extension rather of degree n, then there exists the degree number, so n, distinct K-monomorphisms from L into n. Okay, so we get n total K-monomorphisms from L into n, the degree number of them. And actually, before the proof, we actually already saw this. So as a quick example, just keeping the same example we've been doing, we had Q adjoin alpha over Q, where alpha was a real cube root of 2. And we found that the normal closure was add in a primitive cube root of unity omega. And there were the degree of Q adjoin alpha over Q is clearly 3. And we wrote down, we had these phi's, phi 1, phi 2, phi 3, were our monomorphisms from Q adjoin alpha to n from some of the previous videos. We found exactly 3. And what did we do? Well, we picked where to send the conjugates of alpha. That's basically what we did. And there was, there was exactly 3 of them. The proof is going to mirror this example slightly. So let's get started with the proof. We're going to induct on the degree. If L over K, if the degree is 1, so the degree of L over K is 1, well, then L equals K equals N, because the normal closure of is obtained by adding in the roots of the minimal polynomial of a basis. But if L is K, there's nothing to add, right? Because there's no conjugates because you haven't added anything new. And there exists exactly one K monomorphism from K to K, because we have to fix K, so it has to be the identity. It's just the identity. There's no more than that. Okay, so the degree is the same as the number of K monomorphisms. So nothing to do there. Suppose that the degree of L over K is bigger than 1 now. It's some little k which is bigger than 1. And let's take some alpha in L that's not in K. So L but not in K. And let's suppose it has minimal polynomial m over K. Then we know that the degree of m is the degree of this extension is some r bigger than 1. It's going to be bigger than 1 because alpha is not in K. So the degree of the minimal polynomial is at least 2. Since m is an irreducible polynomial with a 0, alpha in L, remember n is our normal, alpha in n, alpha in L which is contained in n, and n is normal. Remember, n is our normal extension, or our normal closure is normal. N over K is normal, let's say it like that. We know that it has all the other zeros. It splits in L, in n. And we also know that zeros are distinct because we're over C. Let me label them. There's R of them and they're all different. This is not true in positive characteristic unless you're separable. Are distinct. So R, one second. Okay, so then the degree of L over K of alpha is just the degree of L over K divided by the degree of K adjoin alpha over K. And let's see, that's going to be K over R. Let's call that S. What do we know? We know that R is bigger than 1. So we're dividing K by something that's bigger than 1. So this quantity is less than K. Okay, so by induction, there exists S distinct K adjoint alpha monomorphisms. From L, what are we going to call these? We're going to call these row 1 through row S. From L into N. Why? Well, L over K adjoint alpha is an extension of degree less than K, so we can apply induction to it. And we get exactly S, and that's all there are. So these rows, they fix K adjoint alpha. Okay, so they don't move K adjoint alpha. And so what we want to do is also look at the monomorphisms that move K adjoint alpha. Okay, now we saw that whenever you have conjugate roots, there's always an automorphism of the splitting field. The normal closures are splitting fields that send the roots to the other. Send a root alpha to any of the others. So we know by one of the propositions we proved, by proposition, there exists R distinct K automorphisms. R is the same number as the alphas. Automorphisms tau 1 through tau r from n to n. Right? And these guys are constructed such that they send alpha to alpha I. Right? Alpha 1 rather to alpha I. Because these are conjugates from the same they're conjugates. Okay, so let's then set phi ij to be tau I rho j as maps from L to N for 1 less than or equal to I less than or equal to R and 1 less than or equal to J less than or equal to S. And let's also notice this is composition. There are R times S. S was K over R. So there's R times K over R equals K, which was the degree of L over K, such phi ij. And they are all L automorphisms. Sorry, they're all monomorphisms from L into N that are the fixed K. So these are all K monomorphisms. Okay, we need to show two things. We need to show that they are all different, and this is all of them. Okay, so we claim first that phi ij are all distinct. Suppose not. Well, suppose that you had two that were equal. So phi ij is phi kl. All right, let's write out what that means. Phi ij is tau I rho j, and phi kl is tau k rho l. All right, now here, the taus are automorphisms of n, so it makes sense to end with an automorphism of n. And the rows are mappings from from L onto their image. And so, although it's a little bit weird to write rho j inverse, we can write rho j inverse as long as we're careful with what we mean by that. So rho L compose rho j inverse. And rho j inverse is a mapping from the image of L under rho j, and let me just make sure. Hang on, I'm confusing myself. Okay, yeah. So rho j inverse we can view as a map from rho j of L back to L, and then rho L will map you back to N. And really on the left-hand side, I don't mean off the bat, I don't mean these as a map from N to N. I want to view this as a map from the subfield of N to N. Okay, so as mappings like this, rho j inverse makes sense. And rho L composed rho j inverse of alpha is the same as tau k inverse composed tau I of alpha. But the taus are k adjoint alpha monomorphisms, right? Or no, wait, the rows are k adjoint alpha monomorphisms. So the left-hand side is just alpha. They both fix alpha. The right-hand side is tau k inverse of tau I of alpha. And then if we apply tau k to both sides, we get tau k of alpha equals tau I of alpha, which since the taus are determined by what they do to alpha, the fact that these guys both do the same thing to alpha, this tells us then that I is equal to k. Whew. All right, great. Now what? Well, our rows are k adjoint alpha monomorphisms here. Great. And we know the taus are the same. So let's see. Let's go back up here. Yeah, the taus are the same. Both of the taus have to be equal. So we can take this equation, tau I rho j equals, okay, instead of writing a tau k, I get to write a tau I rho L. But we can apply tau I inverse to both sides, and we get rho j is rho L, and therefore j is equal to L. Thus, phi ij, well, thus I is k and j is L. So that's it. Thus they're distinct. So the only time they could be equal is if the indices were the same. Thus, let's be more specific here, the phi ij are distinct. All right, sorry, it was a little convoluted. All right, so we have k distinct monomorphisms from L into N, and we need to now see that this is actually all of them. So to see we have all of them, I'm going to say are exhaustive. Suppose you have another one. Then tau of the same alpha from before, where we wrote down all the conjugates, is still a 0 of m, because the coefficients of m were in k, and tau fixes k. So tau of alpha is some alpha I. Hence, tau I inverse composed tau of alpha is just alpha, because tau sends alpha to alpha I, tau I inverse sends it back to alpha. Thus, tau I inverse composed tau is a k adjoint alpha monomorphism, because it's certainly still a monomorphism from L into N, and it fixes now alpha. But we wrote down all of them, right? We had all the whole list of the k adjoint alpha monomorphisms. They were rho 1 through rho s. Thus, there exists j such that tau I inverse composed tau is rho j, and this is equivalent to saying tau is tau I composed rho j is one of our phi ij's. Okay. All right, so this was kind of a long proof. Make sure to go back and maybe look at this again. Also look at it in your book, although I think I wrote out a bit more than what's in your book.